This week I've got one more integration technique for you. It's known as trigonometric substitution. This is just a special case of U substitution that helps us integrate roots of quadratic expressions such as those you see there. Even though we don't see any trigonometric functions in these expressions, if we use the right trig functions, the integration actually becomes easier. And this is one of the reasons why I think it's important that you learn how to do these techniques by hand, even if you ultimately end up using software to find your integrals for you. If you were to type in any one of these integrals, you would not necessarily expect that the result would come back with trig functions in it. In fact, that would probably be a surprising result. But if you've done these techniques by hand, you know that is something to expect to have happen when your integral looks like this. So you have a table of trigonometric substitutions. It's as if someone has already done the hard work for you and found the patterns that occur. So you can see there are three different radical forms, and each one has a corresponding substitution. So what we're going to end up doing is changing from an integral in terms of x to an integral in terms of t. And because we're making that variable switch, and this is going to at times involve using inverse trig functions, technically you have to be mindful of the proper t domain, and you should only allow your integral to take on those values. In practice, in terms of what you do to integrate, it does not change anything. So I've broken this process down into steps. Ultimately, we're now going to look at integration problems that take up pretty much one whole sheet of paper. So it is important to kind of have a bit of a roadmap, and you're going to notice I'm going to have kind of my main workspace, and I'm also going to have some space off to the side. There's a lot of figuring out of things you have to do as you go through the process to help you make it all the way through the integration. Our first example, example 6 and 7, asks us to integrate, and I gave you a definite integral. Please remember it makes no difference whether the dx appears in the numerator of the fraction or if we put it at the end and instead let the numerator be 1. Those are equivalent. And for the beginning of this, I'm going to just ignore those limits of integration because I just want to focus on the process at this point. And then at the very end, we'll go back and talk about how you would make your substitutions for that. So step 1 here is to identify the radical form that you have. Now it can appear in a fraction, it doesn't have to appear in a fraction. If we compare the format of our radical, it has addition in between two terms. So we're looking to follow this middle row of the table. We have this format. Keep in mind addition is commutative, so it doesn't matter if the x squared is first or last. And it tells us here that the proper substitution to make is going to be to choose x to be a tangent of t. Now, your a value, you always want to consider the thing attached to your x squared as an a squared. So in my particular case, my a squared, the thing attached to my x squared, is a 4. And so we know by taking the square root that a would be 2. And the proper substitution, again from the chart, says to let x be a tangent of t. So I'm going to substitute 2 tangent of t. And not only do you need to find out what x is, which we're going to substitute, we also need to find out what the dx should be replaced with. So we're going to take the derivative of x. 2 times tangent of t, we can just leave the 2 there. And the derivative of tangent is secant squared. So we get secant squared t dt. So again, this is kind of my work off to the side space. Now I'm going to go to the main problem, and I'm going to begin to manipulate this integral. And again, I'm going to just drop my limits of integration for the time being. So this integral, it's like performing a U substitution where I match things up. My dx, my numerator, should now become 2 secant squared t dt. My denominator is the square root, and I'm going to keep that square root symbol in there, of x squared plus 4. So if this is my x here, then I'm going to need to square that. And when you square the left, because you've got a product on the right, you square both of these parts on the right. So I'm going to have 2 squared times tangent squared t, and then I need to keep the plus 4. So this is now where my integral stands. I'm going to do one quick simplification in the bottom of the fraction. And now the next thing I'm going to want to do is under this square root, I've got a common factor of 4. I want to factor that out, and you'll see the magic that happens as a result. So by factoring out the 4, I'm left with tangent squared t plus 1 in parentheses under the radical. And there is a product rule for roots, which says if you have the product of two quantities underneath one square root, you can separate them into separate square roots. So you're going to notice then what occurs is I've got my 2 secant squared t dt still just hanging out in the numerator. And I'm now going to have a factor of 2 in the denominator, and I have underneath the radical tangent squared t plus 1. Now, this is the next place where the same kind of thing should happen each time you do this. There's an identity that allows us to change tangent squared t plus 1 into a different expression. Remember, tangent squared t plus 1 equals secant squared t. Is one of our identities. So again, I'm kind of going off to the side here. Sometimes you might have to move things around in the identity to match what you have in your integral. But this is perfect. Tangent squared t plus 1 is secant squared. So in the next step, I'm going to drop out these constants of 2. So I now have the integral of secant squared t dt, and underneath the square root, I also have a secant squared. And this is the beauty of the trigonometric substitution, is I'm now going to have my radical disappear, because when you take the square root of something that is squared, they cancel each other out and just leave you with whatever that base was. So I still have a numerator of secant squared t, but in my denominator, I now have just secant of t dt. So that is the point of the trigonometric substitution, is by going through these steps, all of a sudden now I've gotten rid of the radical, which makes my life at least a little bit easier. And now when you have secant squared t on top and secant t on the bottom, you can cancel this one secant t with one of them that's in the numerator. So my integral really just becomes the integral of secant of t dt. This is a basic integral rule you should add to your list of integral rules that you kind of keep handy. Secant of t dt is always equal to the natural log of the absolute value of secant of t plus tangent. So in the very next step then, I'm going to be able to integrate. So I'm now at that point where I have a simplified t integral. I'm going to integrate it as natural log absolute value secant of t plus tangent of t. Now you need to look at the big picture and say, okay, I integrated, which was, the point of any technique is to get you through that integration step. However, I am sitting here staring at an answer that has t's, and t is not the variable of the original integral. So I now need to come up with a way to change these expressions in terms of t back to things in terms of x. And the way we're going to do that is going to involve another one of these going off to the side and doing some figuring. I'm going to draw a right triangle. We're actually going to go back to our right triangle trig. you're going to go back to the step where you wrote out what x was equal to and use that to label your triangle. Here's how. You're going to want to get this coefficient off of the tangent. So we're going to divide both sides by 2, giving us x over 2 equals tangent of t. Now you want to remember from right triangle trig the mnemonic device that most people use, which is Sohcahtoa. That tells us that tangent in particular is the ratio of the opposite side over the adjacent side. So I'm going to put t into my triangle, and I'm just going to choose to put it here. And this fraction then tells me that x is what I should label the opposite side from t. So I go directly across from t and I label it with an x. And the bottom, the 2, is the adjacent side. Again, because tangent is the ratio of opposite to adjacent. So 2 should be adjacent to angle t, which is this side here. Remember, the longest side is always the hypotenuse. The next thing we're going to do is solve for that hypotenuse. You can use Pythagorean theorem here. Remember, a squared plus b squared equals c squared. I'm going to put in 2 and x as my a and b. My c, my hypotenuse, is what I'm solving for. So I get 4 plus x squared is my c squared. And I finish by taking the square root. So I get 4 plus x squared equals c. So that's the correct label for the hypotenuse side. Now, why am I interested in that? Because I now can write any trig function I want to in terms of t by using this reference triangle. So you can see in my integral, I'm supposed to fill in secant of t and tangent of t. All right, first of all, let's do the simpler one. Tangent of t, we already know, is this. So tangent of t, we're just going to replace with x over 2. Now, secant is a little bit trickier. You have to remember that cosine of an angle is always adjacent over hypotenuse, and secant is its reciprocal. So secant of t should be the hypotenuse over the adjacent. So my secant value will be my hypotenuse, which I forgot to put my plus sign in there, square root of 4 plus x squared all over my adjacent side, which is 2. So I have the 2 pieces that I need in particular to substitute over here into my antiderivative. That substitution would be the next step. So I have natural log. Secant of t is the same as the square root of 4 plus x squared over 2 plus tangent of t is x over 2 and then plus c. And if this was an indefinite integral without any limits of integration, we'd be done. However, in this problem, we did have limits of integration. So if that's the case, then there's just that one additional step of saying, okay, so this is my antiderivative, which I'm supposed to evaluate from 0 to 2. And you want to go ahead and use your fundamental theorem of calculus to make those substitutions. After you've substituted 2 all the way through the expression, you then substitute 0, and you will simplify as much as possible. So 4 plus 2 squared is 4, so I get square root of 8 over 2. 2 over 2 reduces to 1, minus natural log. On this side, we have the square root of 4, which is 2 over 2, which reduces to 1. And then plus 0 over 2, so I'm not going to add anything to this. And I might make my 1 fancy just to make that clear. There's a 1 in there. Back inside the first one, I can reduce the square root of 8 because the square root of 8 is the same as the square root of 4 times the square root of 2, taking out that perfect square factor. So I can make this 2 square roots of 2 over 2 plus 1 minus The natural log of 1, what exponent do you put on a base of e to have it equal 1? Is 0. So that term's just going to completely disappear. I can cancel the 2's in the first expression, and my final answer for the definite integral is the natural log of the absolute value of square root of 2 plus 1. So again, step back and take a look at all the work that goes on. There's going to be a lot of work within the integration problem, but also a lot of figuring that happens on the side. So give yourself space. Do not try to just cram everything in for the sake of your teacher, please.